Improper integrals. Let's look at convergence tests now. In general, you cannot find the closed form of an antiderivative of an integral. It's similar to, in general, you can't factor a quadratic. So for an improper integral, the first step is to see if it converges or diverges. If it diverges, then you're done. There's nothing else to do. If it converges, then you can apply some numerical method to get an approximate value. That's when we did RAM stuff, LRAM, RRAM, a Riemann approximation. This is a basis for what we're going to be working on because we're going to see if the thing converges or not, the integral. The primary tests that we're going to be using right now for convergence divergence are the direct comparison test and the limit comparison test. So let's take a look at the direct comparison test. If I have two functions and I say, let's go this one, and I'll call that one f of x, and I have this one will be g of x. This says if they're continuous functions on an interval a to infinity such that f is greater than 0 and g is greater than f. So we could say that for all x greater than a, it doesn't mean that it has to be for all values period, but all x greater than a, so we could make this our a value. Then, if g of x, the above one, converges, then f of x must also converge. Or, if f of x diverges and g of x is above it, then it must also diverge. And thinking about these integrals as area under the curve. So if the area under the curve here is infinite, then the one above it will also be infinite. And similar, if this area is finite and we have something smaller than it, then it will also be finite. Often the function we're going to compare to is 1 over x to the p. And here are a couple of graphs. The middle one is 1 over x. This one over here in red is 1 over square root of x. And the one in black is 1 over x squared. Basically, I'm not going through all of it. We did a couple of these in the last video. But the 1 over x graph is the cutoff graph. Below it, the function converges, and that makes this pretty special, and above it, the function diverges. So I did that, so it would be a good idea for you to go through and maybe do I in this first one and 2I over here for the p-values and actually convince yourself that that really is true. All right, limit comparison test says if f and g are both positive and continuous on a closed interval, or actually the closed at a, open at infinity, and if the limit as f over g equals L, where L is some positive number, then both of the integrals from a to infinity either converge or diverge. So it's basically saying that if the functions grow at the same rate, and this is what we did in a previous section, then their integrals from a to infinity behave alike. They behave in a similar way. That doesn't say the integrals will have the same value, but if one converges, the other will converge. If one diverges, the other will diverge. Let's look at a couple examples. Zoom in a little bit. So we have here, I'm going to go through both the direct and the limit one for each of these. So if I'm looking at direct, I have, one thing I want to realize, I have a trig function here, and that we know that sine x is less than or equal to 1 for all x. I forget if I've gone over this symbol. This just means for all. So for every x value that's true, that means we can compare this to 4 plus sine x over x cubed is going to be less than or equal to always 4 plus 1 or 5 over x cubed. So we know that this original integral will be less than or equal to, and I'm going to just pull out the 5, so I'll say 5, and we're going from e to infinity of 1 over x cubed dx. So then when we're looking at this one, we can say this converges. Why? Because p equals 3 on this interval from e to infinity. So if this one converges and the original one is less than it or equal to, the original one also converges. So the direct comparison test would say, yes, we're guaranteed this converges. We don't know what it converges to, but we can apply some approximation. Let's take a look at the limit as well. We need to find a function to compare it to. Let's use the same one, 1 over x cubed. So we'll find the limit as x goes to infinity of 4 plus sine x over x cubed divided by 1 over x cubed. And then when we flip and multiply by 1 over x cubed, those will reduce out, and we get 4 plus sine x. And that does not exist since it oscillates. Since that doesn't exist, this test is inconclusive. It doesn't tell us anything. It doesn't tell us if it converges or diverges, but we know by the direct comparison test it did converge. All right, let's look at the next one. E to the negative x over x. So the direct, so when we're looking at this, on the interval from 1 to infinity, we can say e to the negative x over x is less than or equal to e to the negative x, well, over 1, because as x gets bigger, this overall fraction gets smaller. And that equals e to the negative x. So we can look at the integral of e to the negative x that has a limit of a negative or a positive infinity. So let's go ahead and find this. The limit as b goes to infinity, the integral from 1 to b of e to the negative x dx. Find the antiderivative. Let's carry this over. B to the infinity. And then that would be negative e to the negative x, evaluated from 1 to b. Limit as b goes to infinity. I think I can squeeze it in. Negative 1 over e to the b plus 1 over e. You could write negative e to the negative b, but it's a little bit simpler there. And what does this equal? As b goes to infinity, e goes to infinity, that fraction goes to 0, and we're left with 1 over e. So the original one is less than or equal to the integral from 1 to infinity of e to the negative x dx. And since that equals 1 over e, the original one converges. Let's look at the limit. We will look and say g to the x equals e to the negative x. Just like we looked at before, we're going to look at what function is going to be the dominant one here. So we'll have the limit as x goes to infinity, e to the negative x over x divided by e to the negative x. That equals the limit as x goes to infinity of 1 over x. That equals 0. And what does that tell us? You can take a look at that, the limit comparison. It tells us nada. This is inconclusive. Why? Because that limit has to be a positive number. It has to be greater than 0, less than infinity. So it's inconclusive. L must be a positive number. Okay, next one, number 3. When we look at this, there's two issues. One of them, it's undefined at x equals 0, and we have a limit of negative infinity. So what we're going to need to do is break this up to deal with both of those separately. We will so we can have each one of those issues in a separate integral. So let's go negative infinity of dx over x cubed. Now we need to pick some number in between that's convenient for us. So how about -1 dx over x cubed? Let's deal with, let's put an equals there. Let's deal with these one at a time. So we will go -infinity. Actually, I don't want to put an equal here. We'll just deal with this one. -infinity to -1 of dx over x cubed. Now all of our stuff is dealing with positive values. So by symmetry, this is going to equal negative from 1 to infinity of dx over x cubed. Now this one converges because p equals 3, and we're dealing with this interval from 1 to infinity. Let's look at the next one. We have -1 to 0 dx over x cubed equals negative, and we'll go 0 to 1 dx over x cubed. Now this one diverges because p equals 3 on the interval from 0 to 1. So if this one diverges, the whole thing diverges. The original one diverges, and we're done. All right, the next one. So this one we're just dealing with integration on there. On the next one, when we look at this, we have to take into account the fact of this interval here. We're going from 0 to pi over 2, and on that interval we can guarantee that cosine of x is greater than or equal to 0. So by the direct comparison test, we can say the square root of x plus the cosine of x is greater than or equal to just the square root of x. We're trying to look for a simple function to compare it to. Remember, if if one fraction is bigger than another, if one number is bigger than a number, for example, 3 is greater than 2, then if we find the reciprocals of those, 1/2 is greater than 1/3. So what happens when you find the reciprocal is you flip the direction of your inequality. So we have 1 over root x plus cosine is less than or equal to 1 over root x. So now let's look at that one just like we did before. 0 to pi over 2 of 1 over square root of x, or x to the 1/2 dx. Now that one converges because p equals 1/2 on the interval from 0 to pi over 2. So we're looking 0 to some constant there. So if that one converges, this says the original, which is less than this, converges. Let's pull out that 3 and deal with a simpler function. We have 10 to infinity of dx over square root x to the 4th minus 2. Now where the denominator would be 0 is not going to be inside this limits here. So the only thing we have an issue with is infinity. Let's compare. First, we can start off by saying x to the 4th minus 2 is guaranteed to be less than or equal to x to the 4th. So if we take the square root of both sides, that will still be true. And just like we did on the previous one, if we take the reciprocal of this, we have 1 over root x to the 4th minus 2 is going to be greater than 1 over square root of x to the 4th, and that can simplify to 1 over x squared. Now if we look at just that one, 10 to infinity of 1 over x squared dx, that converges because p equals 2 on that interval from 10 to infinity. Now, the original is greater than this. than this. So what does that mean? That means this is inconclusive. Why is it inconclusive? Well, we know that the one we're comparing to converges, but the ones above it, we don't know if that's going to converge or diverge. So it really doesn't tell us anything. As a little aside, if I change this to a plus, then this would be greater than on this side, and we flipped it to be less than, then we could guarantee it does converge. But we can't do the direct on this one. So let's try the limit. On the limit, we're going to use that same basic function, 1 over x squared. We have the limit as x goes to infinity of 3 divided by the square root x to the 4th minus 2 divided by 1 over x squared. And that is the limit as x goes to infinity of 3x squared over that square root. Now in one of the previous recent videos, we just did a problem similar to this. We could factor out that x to the 4th and do it properly, but basically this is going to behave like x squared, so this limit is 3. So what does that mean? Since from 10 to infinity dx over x squared p equals 2 converges, so does the original. So on this one, the limit test worked, but the direct did not. And let's look at one more over here. So on this one's a little bit different in that we have this subtraction going on here, and we need to find all the issues. So the issues are x cannot equal, or is at x equals negative 2, x equals negative 4, and a limit of infinity. But x equals negative 4 is not inside the limits that we have here. So what do we need to do? Just like we did before, we need to break it up into two separate integrals. I go negative 2 to 0 of 1 over x plus 2, 1 over x plus 4. Let me make sure I write that correctly. Plus, we're just picking some convenient number. We could use 1, we could use 0. It doesn't really matter because there's no problem in between. So just like we did before, let's deal with one part of it. So let's deal with this first part. We're going to find the limit as b goes to negative 2 from the right-hand side of b to 0, 1 over x plus 2 minus 1 over x plus 4 dx. Go ahead and find that, the antiderivative of each one of them. So the antiderivative will be ln of the absolute value of x plus 2 minus ln x absolute value of x plus 4. And we're going to evaluate that from b to 0. Let's come back, and since on this interval these values are positive, we don't need the absolute value there. So we can just write the limit as b goes to negative 2 from the right side of the ln of the quotient x plus 2 over x plus 4. Still need to evaluate it from b to 0. Let's try to do that now. Negative 2. So when we plug in 0, we get ln of a half minus the ln of b plus 2 over b plus 4. Now we need to do that one. We have ln of a half is the same as negative ln of 2. Same thing as ln 2 to the negative 1, bring down the negative, minus the ln. So the top is going to be going to 0, but it's going to be going to 0 from the positive side, and the bottom is going to a constant of 2, so that won't affect it. Still going to be 0. And recall, we have our ln graph. As x goes to 0, this graph is going down to negative infinity. So we have negative ln of 2 minus negative infinity. That gives us positive infinity. So this one, the original integral diverges. And we don't need to deal with the second one at all. We're done. All right, let's take a look at summarizing what we just did and these different tests for the different problems. So we have on problems number 1 and 2, the direct worked, but the limit did not. On number 4, both worked. On number 5, the direct worked, or did not work. Sorry, did not work. But the limit did work. So, and the other 2, the 3 and the 6, we did just by evaluating the integrating it. How can you decide actually, I want to stop back for one second. So how are you going to know which one to use? You really don't. What you need to do is, with more practice, you get better at it. But you can't necessarily just look at it and say, oh, it's this test that's going to work. And you know it as you're doing it. So if one works, great, you're done. You don't need to do both. I just did both to help you to show both of them. And if one doesn't work, then you try the other one and see if that does. How do you decide the function to compare to? I was getting a little ahead of myself. Remember, FCN is just function to compare to. Go ahead and write these down. If you have sine x, cosine x, you replace it with 1, since that's the max value of it. For number 2, if you have a constant or lower powers within an expression, then you want to just get rid of them. So for example, on question 5, we had x to the 4th minus 2. That 2 is not affecting it, so just get rid of it when you're thinking about that dominant function. And even if it said x to the 4th minus x cubed, you would still drop off the x cubed to get a simple function to deal with. Simplify the remaining. So 1 over x to the 4th, we simplify to 1 over x squared, and then use the p on the interval. And then the third one, use your knowledge of what functions dominate, as we did in problem number 2. All right, so you got those 3. Then we have, here's another one. It's just extra practice for you to do. Take a look. If you want to do it, stop right now, and then I'm going to put up the solution. I will assume you did. And here is the solution. Zoom out a little bit. Okay. So when we look at this, I just wanted to review our integration by parts. And this is a tabular integration, so fairly straightforward. Once you remember how to do it, we evaluate, because the only issue on this one would be the infinity. And we get a value of 2, so that says it does converge, and we're done with that. And that is enough.